Okay, so we're really going into this equation here, and I talked to you about units of, or talked to you about what S is, and let's talk about the units. Okay, um, in SI units, entropy is going to be heat, which is kilojoules per temperature, Kelvin, and note, excuse me, it's always in absolute here, always in absolute. This is a ratio. It's important that because all this entropy was tied back to, Kelvin, we got to use absolute scales. That's how it was determined. So we have to make sure we use absolute scales here. We can talk about a lowercase s. And you know what? If we have a lowercase, we had capital U for internal energy and lowercase u, capital H for enthalpy, lowercase h. We're going to have capital S and lowercase s. We know that that's going to be kilojoules per Kelvin, and now we have to have kilograms Kelvin, okay? And if we wanted to, we can do S bar, which is going to be in kilojoules per kilomole Kelvin, right? Just think we have English engineering units, okay? S is equal to BTU per degree Rankine. Okay. And lowercase s is going to be BTU per pound mass per degree Rankine. And S bar is going to be in BTU per pound mole per degree Rankine. Okay. And we can use entropy just like we did with specific volume and internal energy and enthalpy. They all can be found in the tables in your book. In fact, that's the last column that's available there. And we can now open that up, and we can use that S is equal to SF plus X times SG minus SF. So let's take a look at that. Here, let's open up our document camera. And here we go. And it's like we're doing an achievement, and we've now unlocked this last column, entropy. Saturated liquid, saturated vapor, just like we had specific volume and internal energy. Okay, that's what we have. I'm playing, I'm with my kids, I get 15 minutes a day that I can play Super Mario Odyssey on the Switch. And I get to unlock these worlds, and I get to do all this thing. And the kids are working on it too. They're working on their own little thing. They work together, and it's great. It's great. I'm a hardcore Super Mario gamer, and we get to unlock these achievements, and it's very, very exciting. You know, we talk about it all day that we're going to do that, and you've probably been talking about this all summer semester. When do I get to unlock that last column? It's today. Today you get to do it. Very, very happy. Very, very excited for you. Okay, entropy is in the superheated water vapor tables too. Same thing there. You're going to see it's going to have a lot of digits here. We're going to have some interpolation that we're going to have to deal with. Sometimes we deal with entropy in the problems in our book, because we have 4 decimal places. We have to be very careful with our significant figures that we're dealing with. But just note that's we're going to keep those 4 decimal places. Okay. We can also make, the liquid approximation that we talked about here. Liquid approximation. Okay. What was a liquid approximation for everything? It was, if you give me the temperature and the pressure, I can approximate this to equal the saturated liquid at whatever temperature I'm at. So it's really no big new news that we're dealing with. Okay. There are a couple tables, and you're not going to really use this in this class, but I want to show them to you so that you're familiar with them. This figure in the back of your book is a temperature entropy diagram for water, and it has entropy on one axis and temperature on the other axis. It has all these pressures, and this is called a Moody chart. Okay, a Moody chart, and these are very valuable charts when you're going to start working with power cycles and things of that nature in steam power plants. These Moody charts, a lot of lines. We're not going to look up things in these charts. Temperature enthalpy diagrams, enthalpy entropy diagrams. There's also this enthalpy entropy diagrams sorry. I said Moody chart, and I'm sorry about that. That's fluids. Friction is Moody chart. This is just a simple temperature enthalpy entropy chart. This is called a Moliere diagram. Sorry, man, Moliere diagram, enthalpy entropy Moliere diagram, and you'll use this a lot in power plants, and it will really save you some time. But it's not going to be as accurate as using the tables. Okay, so those are Moliere diagrams. So figure A7 and A8. That's what you'd use those for. We're not going to use them in this class, like I said, but I want you to be aware of the Moliere diagram. Moody chart is about friction factor in pipes, and that's in fluids. Dr. Wanklem, this is where I miss you guys. I miss you guys yelling at me in class and telling me, hey, you said something. Doesn't make any sense. So there we go. Those diagrams. All right, now, I have sad news to report with all this. We're talking about entropy, and the sad news is that if we understand these laws here and entropy generated, and that when we go from place to place, we generate entropy and we can't have any negative entropy, and I'm going to tell you, in order to have time travel, you would have to break the second law of thermodynamics, and it just doesn't look like that's possible. So if you've read on Facebook that there's a person that's traveled to 2035 or whatever and found out that I don't know, that the coronavirus is still going about and I don't know what's happened, that person is likely wrong, and it's all because of second law of thermodynamics. So I would just mainly the comments on Facebook when people are posting these things are very kind. I think you've noticed the world's a very kind place. People, when they disagree in a very kind way these days. But you could kindly disagree and say, my professor said that this is impossible because of the second law of thermodynamics, and just see what the response would be. Probably a lot of playful banter and chatter coming along there. All right, let's go back to our equation here. Let's go back to our equation and think about it a little bit. Because you're going to be doing this equation here, this S2 minus S1 is equal to the integral from 1 to 2 of dq over t plus sigma. This is going to be what you're going to do on your homework tonight. I'm going to say we can write this way, delta S is equal to, and I'm going to replace this integral with the summation of heat transfer and the temperature at which that heat transfer occurs, and I'm going to put temperature of the boundary plus sigma. This is the way you're probably going to use it more often. Delta S, just like delta U, just like delta H. This is going to be mass times S2 minus S1, if you look at it. And then I replace the integral with the summation, because we're not going to have a lot of systems that we're going to have a varying heat transfer that's going through a varying temperature that boundary that is crossing. Okay, we're going to have a heat transfer, and it's going to be crossing into our system at some temperature, and this is going to be the temperature of the boundary. So we're going to look at the heat transfer and the temperature of the boundary that the heat transfer crosses. Okay, this is going to be an absolute temperature. Now, of course, you are going to have situations in real life that there's going to be a surface and there's going to be a varying heat transfer coming into that surface, and that surface boundary that you're looking at is going to be changing with its temperature. But those are more complicated problems, and we're not going to deal with those right now. We are going to simplify them largely here. So I'm going to see you're going to be dealing with this a lot. Mass times S2 minus S1 is equal to the summation of the heat transfer, the temperature at which that heat transfer occurs, plus sigma. Okay, you're going to just write that equation a lot and see how that works. And this will work in conjunction with the first law. The heat, if you solve for Q in this law, that Q can go into the first law. If you solve for heat transfer in the first law, that Q can come into this law. These can all work. Okay? Now, often what you're going to hear is things like, what is the maximum amount of heat that can be transferred, or the minimum amount of heat that can be transferred? When you hear this maximum and minimum type of language, what should you think of? Well, you should think of that maximum means, or that minimum, depending on how the situation arises, that it means that the system is operating at its peak. It's ideal. And so that's when we'll have situations where this would go to 0. Okay, so let's look at entropy change in internally reversible processes. We talked about internally reversible processes, what they are. We said they are real. We can deal with those. Okay. So if we have that situation, what we're going to have is delta S is going to be equal to the summation of the heat transfer and the temperature at which that heat transfer occurs. And really, quite frankly, we're often just going to have one heat transfer that we're going to deal with, so we don't have to worry about a summation. It's going to be one heat transfer. Okay, so let's look at what this equation is telling us. The energy and the heat transfer, okay, this means that a system has some energy by heat transfer. That means if we add heat transfer to a system, heat transfer into a system, what's happening to our delta S? It's going to go up. If we remove heat transfer from a system, delta S is going to go down. So the direction of the heat transfer determines whether you're going to have an increase or decrease in that entropy of the states. Okay, so entropy transfer accommodates heat transfer. The direction of the entropy transfer is the same as the direction of the heat transfer. Okay, now, notice what would happen here if I would also say the system is adiabatic. And it's reversible. Okay, we already dealt with reversible to get to right here. But what if we said it was adiabatic? Adiabatic would mean that this goes away. And what happens? If adiabatic and reversible, now our equation comes down here to this. Delta S is equal to 0. Delta S is equal to 0 is something that we call isentropic. Entropy does not change. It's isentropic. Like isothermal, it's isentropic. Okay, so therefore, what I want you to remember is this triangle. Okay, if a process is adiabatic, if a process is reversible, it means that process is isentropic. Okay, and the great thing about this triangle is any two sides of this triangle infers the third side. So an adiabatic isentropic process is reversible. A reversible isentropic process is adiabatic. We can infer the third side. Okay, so I've told people this, and I'm kind of serious about this, that I want to come up with my own line of clothing. So you know my two big goals. First of all, I want to buy 101.3 a radio station and constantly just talk about what atmospheric pressure is and to the masses. That's what I want to do. That's my first lifelong goal. My second goal is I am going to create a line of clothing, thermodynamic clothing, that I was going to call wankwear, and this I would make a shirt that had this symbol on it. My wife does not necessarily think that calling a clothing line wankwear is a very good idea, but you know it's my idea, and someday by the grace of God I'm gonna do it. But that day is not today. So anyway, let's pause here and we'll go on to our next segment.